Hi, Algebra 2 honor students. This is Unit 16, Day 7. Today we're going to do some more work with double angle identities. And my main focus today is going to be on solving equations and proving some identities. So less of just the straight up algebraic situations where we sub into one of the identities based on a triangle in one of the quadrants, but more of a solving situation or some proofs. Now, if you're feeling pretty confident about identities, in theory, at this point, you could hit pause, copy these 5 examples down, and try them on your own if you want to challenge yourself. If you're like, well, I'm not quite there yet, well, then stay tuned, and we're going to go through the solutions to each of these in the video right now. So we're going to solve the equations over the interval 0 to 2 pi. The identities we'll prove at the end of the lesson. So let's get right into number 1, which is sine 2 theta minus sine theta equals 0. So to start with this example here, when you see a double angle identity, we have to make a substitution there. And as a reminder, don't confuse sine 2 theta with sine squared. Those do not mean the same thing. Here we're doubling the angle. Here we're squaring the function sine theta. Sine 2 theta has a replacement. It's 2 sine theta cos theta. So you have to replace that whenever you see it. And now that I see what's left, hopefully you're noticing that there's a GCF here. Okay, it looked a little tempting at first to take out a GCF of sine, but with different frequencies, there's nothing in common there yet. But now they both have sine theta in common, so take that out. You're left with 2 cos theta minus 1. And then from there, you can go ahead and separate the factors. So in one instance, sine theta equals 0. Over here, we get cos theta equals 1/2. Sine theta equals 0, we know from the unit circle where the y value is 0, here and here. Cos theta equals 1/2, where cosine is positive in 1 and 4. Adjacent of 1, hypotenuse of 2. So this is a reference that we're familiar with of pi over 3. So putting all the solutions together for theta, theta in the end equals 0 for our initial solution. And then from there, we're going to list the quadrant 1 answer of pi over 3. This quadrantal at pi. And in quadrant 4, with a reference of pi over 3, the answer is 5 pi over 3. Okay, so double angle substitution, go ahead and sub in, and then look for GCF or other factoring techniques to start to appear. All right, in number 2, the equation was cos 2 theta plus 13 cosine theta minus 6 equals 0. All right. For cos 2 theta, this is the one that we have 3 options for. So cos 2 theta, what are my options? Well, you can choose cos squared minus sine squared. So that's one option. We can choose 2 cos squared minus 1 or 1 minus 2 sine squared. So for cos 2 theta, those are the options that I want to be able to draw from. Now, we want to be really wise about our decision. When you're solving an equation, there should be one obvious choice, because if we can, we'd like to rewrite this equation all in terms of the same trig function. And notice how the trig function in the middle here is just normal old cosine theta. So out of these 3 options, I want you to think about which one makes the most sense, so that when I substitute something in here, we just have one trig function we're working with. I hope that the way I phrase that has made it obvious that I'm going to choose the one in the middle. 2 cosine squared minus 1 is the substitution here. Now I'll have an equation all in terms of cosine that I can go and solve from here. So we're going to do plus 13 cos minus 6. Let's go ahead and combine some of these like terms. We have the negative 1 minus 6, which is going to give us a minus 7 at the end. And then hopefully that results in something that's factorable. If not, we have some good quadratic formula skills we can rely on. I think this one is factorable though, right? If you pair a plus 7 over here, that's going to be 14 cos theta, and put minus 1 here, that's negative 1 cos theta in the middle. So that all checks out in terms of factoring. We're not used to seeing large numbers like this probably within our factoring, but we're going to like what happens in a moment here. Okay, cos theta equals 1/2. So that's one side. Cos theta equals negative 7 is the other side. Now, for cos theta equals negative 7, if I'm thinking about adjacent over hypotenuse, definitely no way the adjacent is 7 and the hypotenuse is 1. So this side has no solution, and we can hopefully pretty quickly get there. Cos theta equals a half. I'm going to cheat a little bit because we just did that in the last one. So it's the same exact picture as up here, which leads us to solutions of theta equals, it was pi over 3 and 5 pi over 3. Those are the two solutions that you get when cosine theta equals 1/2. Okay. So I usually don't cheat the process, but since we had just done that situation moments ago, I thought it was okay to do that. All right, let's go ahead and do one more solving cos 2 theta plus sine theta equals 0. And once I go ahead and check out this equation, I'm going to go back to my list for cos 2 theta here and decide which of these three options makes the most sense. When you're solving an equation, I rarely choose that first option because that's going to introduce both cosine and sine in our equation, which is two different trig functions. I can't think of a time that I would probably choose that one when solving equations. Do I choose this other times when I'm doing some algebra with double angles? Yes, I will. But let's see. Well, we have sine theta right here, so I think it makes sense to choose the last option, 1 minus 2 sine squared. Because now I have an equation all in terms of the function sine theta. Okay, so replace that with 1 minus 2 sine squared. I'm just going to do some rearranging here so that I get the sine squared term first, and I want that lead coefficient to be positive. So I'm going to write it as positive 2 sine squared. Going to change the other signs here as well. It's essentially like I'm dividing both sides by -1 to make that happen. However you best rearrange your quadratic. Now we're up to the stage where we can factor 2 sine and sine. All right, can I get -1 sine in the middle? I think I can if I do a -1 here, a +1 there. -2 sine plus sine is -1 sine in the middle. So in one instance, we get sine theta equals -1/2. Over here, sine theta would equal 1. Okay, sine theta equals 1, that's unit circle. It's right up here where the y value is 1, so that's pi over 2 for an angle. And for sine theta equals -1/2, we're going to be in the quadrants where sine is negative, quadrants 3 and 4. And if I label those sides, the reference angle here across from the 1 is pi over 6. So when all said and done for our values of theta, the first solution in order would actually be that quadrantal at pi over 2. And if this is pi over 6, halfway around is 6 pi over 6. So plus that pi over 6 becomes 7 pi over 6. Full circle would be 12 pi over 6. So pi over 6 before that, 11 pi over 6. So the equations aren't too scary once we make a substitution. They're the same equations that we solved in Unit 15 and that we've had a few days of practice with up until this point. So we just have to be confident with, first of all, what are the double angle identities? We'll have to know those. But once I'm comfortable with that, hopefully I can use that list and draw from it right away to plug in to our equation. Okay. Let's do the identity proofs that I had listed at the start of the video today and see if we can show that the two sides are equal when I prove in the first example that sine 2 theta plus sine theta divided by cos 2 theta plus cos plus 1 is equal to tangent of theta. Okay. So we got a lot going on the left side. So if I take a look at the right side just for a moment here, I'm going to just think of tan in my head as sine over cos. Because I see a lot of sines, I see a lot of cosines. So why don't we go ahead and think of tan as sine over cos so that in the end, when I simplify this, I really hope I can get it to look like that, sine over cos. Well, we have two double angle identities in this proof that we're going to have to sub in for. Sine 2 theta. The nice thing about sine 2 theta is there's only one option. It's 2 sine cos plus that sine up top. Okay. On the bottom, cosine of 2 theta is the one that has those three options. I want you to think about which one makes the most sense. Let's check it out. Cos 2 theta. These are the three options. Well, what's my goal? My goal in the end is to hopefully just get a cosine on the bottom. And I see a bunch of other cosines already there. So if I just want to be left with cos on the bottom, I think the one that makes the most sense is the one that only has cosine in it. If you choose one of the others, you'll eventually get to the correct answer. Just might take you a few extra steps. Okay, so I chose the identity that only had cosines in it, and now I'm going to start doing some other algebra steps, including taking out a sine on top as a GCF, which leaves you with 2 cos theta plus 1. On the bottom, 1 and minus 1 would cancel, so those are gone. And notice how the remaining terms, 2 cos squared plus cos, have a GCF of cosine. So if you take out a cosine theta, let's see what that leaves us with. If I take cos theta from here, it leaves me with 2 cos theta, plus take cos theta from there, you get a 1. Whoa, hang on. 2 cos theta plus 1 is a common factor on the top and bottom, which leaves me with sine over cosine. And of course, that is on the other side as tangent. Okay, all my fun symbols, because I'm really excited that I proved that these two sides were equal. I know that I made these look, pretty easy so far. At least I hope that that's the case for you. That's my goal. But it does take some practice to get used to what makes the most sense to sub in. So the last one that we'll do today is the identity sine 2x over 1 minus cosine of 2x. That equals cotangent of x. Okay. So I know that cotangent, similar to what I started with in the last example, is going to be cosine over sine. So in the end, I want to try and break this down so that I get cosine over sine at some point along the way. Okay, let's see if we can make this happen. Sine of 2x on the top, that's the one that only has one option. It's 2 sine cos. Okay. On the bottom, 1 minus cosine of 2x, I'm going to have to replace that cosine of 2x with something. Okay, here's my 3 options again for cosine of 2x. Let's see which one makes the most sense this time. Well, what do I want to have left within the bottom? Just something that has sine in it. So do I have an identity for cos 2x that just has sines? I think I do. It's the last one. 1 minus 2 sine squared is the replacement that I'm going to make. Notice how when I replace cos 2x with this binomial, I put parentheses around it. That will be an important step to include. All right, so we've got 2 sine cos on the top. In the next step, I want you to distribute that negative across to make it 1 minus 1 plus 2 sine squared. And now that that negative is distributed, the 1 minus 1 goes away, and we get 2 sine cos over 2 sine squared. Let's see what happens when I simplify this. Well, first of all, the 2's would cancel on the top and bottom. This sine x on top cancels with one of the sine x's on the bottom to leave you with cosine over sine, which is, of course, cotangent. That's what's on the other side. So again, with some smart substitutions, we get to that result pretty quickly. If I make another substitution, like I said, I was going to get to the same point in the end, but it probably would require a few extra steps along the way. So what we'll do for practice in class next time we're together is some more equation solving with some double angles, certainly some more identity proofs as well. Have a great rest of your day.